kind of math, but it's reading a graph. It's a math topic over solubility. And specifically, we're going to look at solubility curves in today's video. So what we're going to first define is just what is solubility. Then after we define that, we're going to look at a solubility curve graph. So what your solubility is actually talking about is how much solute you have to add to your solvent to make something saturated. But when we make something saturated, we have to remember that it is temperature dependent. It's temperature dependent because as the particles start moving faster and faster and faster, that typically is going to increase the solubility. So when you have a solute dissolved into a solvent, when you increase the temperature, the particles move faster, so they spread out. Remember that supersaturation? And when they spread out, you're able to put more solute into your solvent. Now, this doesn't work with gases, as we're going to find out here in a few minutes. But typically, you have your increase of your solute being able to be added to your solvent. With gases, that doesn't happen because as the particles start moving faster, the gas particles hit one another, it makes bubbles, and as it makes those bubbles, it effervesces faster. So that's why if you have a hot soda and you open it up, it's going to go everywhere and kind of explode is what people call it. And that's because of that solubility. If you have a cold soda and you open it up, it's not going to bubble up everywhere. Same thing if you shake a soda. As you shake it, if it is hot, it's going to really explode everywhere. But if it's cold, it's not going to go as fast. So as you increase your temperature, typically it increases the solubility. Gases are a little strange in this case, that it is not going to affect it. So what we have here is called a solubility curve. And a solubility curve is just a graph that shows your solubility at different temperatures. And I'm moving this over just so you can keep me up here as well, because you all like to look at my face, I guess. But you have your grams over here, and it's the grams of the different solutes dissolved into 100 grams of water. Now, 100 grams of water is the same as 100 milliliters of water. That's going to come into effect here in a little while. But as you're looking at the grams of solute dissolved into your water, each of these lines is a different substance. So it's going to specifically say in the question, for potassium nitrate, how many grams dissolve into, I don't know, at 20 degrees Celsius to make a saturated solution. So the temperature is listed down here. The grams of solute dissolved into 100 grams of water is on the side. We would only look at potassium nitrate, because that's what the question asked for. So I would only look at this line right here. I would ignore everything else on there. If it asks about, I don't know, potassium iodide, we would be, let's see, it's up here. This is my potassium iodide line. So as it asks the questions, it's going to give you a substance, and it's going to ask you the saturation, the solubility, at a particular temperature, because everything is temperature dependent. Now, if you look here, some of these lines look like they're going backwards. So they start high and they get lower as the temperature goes up. That's because they're gases at room temperature, or not at room temperature, at that temperature, sorry. And so when you're looking at the gases, it's how many grams dissolve into 100 grams of water. Sometimes they're backwards because they're gases at that temperature, and gases have a reverse as the temperature increases, the solubility decreases. So that's why some of them go backwards and some of them go forwards. Increase and decrease, I don't know why I'm saying backwards and forwards, sorry. But like this line right here, it starts high and it ends up lower. That solubility decreases as the temperature increases. That's a gas at that temperature. All of these start low and they end up high. So that's the only difference there. So when you're looking at these different solubility charts, we are going to pull as many Sig Figs off of them as we can. So in order to pull as many Sig Figs off of the graph as we can, the 100 grams of water would be 100.0. So these would be 0.0. If you think it's exactly 20, it's 20.0. Again, it's not perfect, but we want as many sig figs as we can when we do the math. So that's why I have you do this, where we're writing it with a decimal place after it. So if you think that something is exactly 25 grams in 100 grams of water, it will be 25.0 in 100.0 grams of water. So always put that 0.0 or 0.5, they'll be 0.0 because they go up by tens on the graphs, just for that sig fig factor. So the reason why we have to look at sig figs is you are going to do some math problems, and it's going to say something about what is the solubility. That means that you're looking at the saturation point. When you are on the line, no matter which line you're looking at, on the line, it means that it's saturated. So that means that you have a fully saturated solution at that particular temperature. So if it says something about, what is the solubility of potassium chlorate at 25 degrees Celsius, that's where you'll start here at 25 degrees Celsius. You'll go up to potassium chlorate. You'll be able to read the graph for your saturated solution. That also means that if you are below the line, you're unsaturated. That means that you can add more to get to that point. And it can ask you things like how many more grams have to be added in order to be a saturated solution. You can actually figure that out. That also means that anything above the line is supersaturated. So that means that they've heated it up, they've added more crystals, they've cooled it back down, now it's supersaturated. So on the line is saturated, below the line unsaturated, above the line is supersaturated. So these are the types of questions that you're going to see with these. And I'm going to swap over to my document camera just so you can actually see what I'm doing with the graph and everything. So let me see if I can do this. This first question, it's kind of cut off. Let me see if I can move it up a little bit. It says, what is the solubility of potassium chlorate at 60 degrees Celsius? So the solubility, when it's asking for it, it just means where is it saturated. So I want to know where is it on the line at 60 degrees Celsius for potassium chlorate. I need to know what potassium chlorate is. Potassium chlorate is ClO3. So that is the only line that I'm going to look at. So when I look at my graph over here, I have my potassium chlorate line, which is this one right here. I didn't trace that very well, but that's okay. So with my potassium chlorate line, I'm only reading it at 60 degrees Celsius. So when I read this, the solubility means that where it is saturated. So I'm going to read the graph right here. So at my saturation point, where my solubility lies, I'm going to cruise over here, and that is, 23 grams? So we're going to write it as 23.0 grams of KClO3 dissolved into 100 grams of water. So you write them like a fraction almost, but it's going to be an equivalency that we're going to use in like a stoic problem dimensional analysis. So that's why we're going to write them this way. We're also going to use them in proportions. So it's 23 grams of potassium chlorate dissolved into 100 grams of water to make my saturated solution at 60 degrees Celsius. A lot of times when people do these, they'll look at them and they try to put the 60 degrees Celsius somewhere in there, and you can't actually do that. It's how many grams of solute are dissolved into 100 grams of water. So no matter what you read off of the graph, you have how many grams of solute are dissolved into 100 grams of water. It's always, always, always written in that way for your solubility. Now this one, we're going to set up a proportion. This question says how many grams of potassium nitrate, so potassium nitrate is KNO3, is needed to make 400 grams of solution at 45 degrees Celsius. So when I look at my graph, I'm only looking at this line right here. And when I look at that line, I'm only reading it at 45 degrees Celsius. That's the only thing that I do with that temperature, is it tells me where to read the graph. So as far as my solubility goes, my solubility occurs right here for 45 degrees Celsius where it crosses the line. So this says that's about 75.0, because you always put the 0.0, grams of KNO3 dissolve into 100 grams of water to make a saturated solution. So that's what I read off of the graph. So this part came from the graph. However, the question doesn't have 100 grams of water. We want 400 grams instead. So when it says grams of solution, that's how much liquid is there. So we're going to make a proportion. So we have 400 grams of water instead, because that's how much solution we needed. I want to know how many grams of water I need to add to it. So we can solve this. You're basically multiplying this by 4 because it's 4 times the amount, but just to show you the whole thing. I'm going to take 75 times 400 is equal to 100 times x. I'm going to solve for x. So when I get my calculator screen is reading 300 at this point. So with that, I'm going to look at Sig Figs. I've got 3 Sig Figs, 3 Sig Figs, 4 Sig Figs, so I need 3 Sig Figs in my answer. So I have 300 grams of KNO3 needed to make 400 grams of solution. So when we're looking at these, we're going to set up a proportion. You're going to take what the graph tells you at that particular temperature and set it equal to whatever's in your question. And then you'll be able to solve for whichever component you need. Now the last one, it says how many grams of water is needed to make a saturated solution using 87 grams of potassium dichromate at 45 degrees Celsius. So again on this question, I'm reading the graph at 45 degrees Celsius, but I'm only looking at the potassium dichromate line. So the K2Cr2O7, that is this line right here. That is the only line that I'm looking at. I'm ignoring everything else. When I read it at 45 degrees Celsius, I'm right here. So that looks like 25 grams. Remember, you put the 0.0 there for Sig Figs. K2Cr2O7. Whatever you have on the graph, however many grams, that's dissolved into 100 grams of water. Now the question says, this is reading the graph at 45 degrees Celsius. The question says that instead of 25 grams of potassium dichromate, I have 87 grams. I'm out of room. Sorry, I'm squeezing that in on the side. I want to know how much water I need in the end. So it's setting up a proportion. What you read off of the graph and setting it equal to what is in the question. Again, the 45 degrees Celsius only tells you where to read the graph. So with this, we're going to take 25 times x is equal to 100 times 87. So I'm going to divide by 25 to get my answer. So I'm going to take 100 times 87 divided by 25. 4 Sig Figs, 3 Sig Figs, 3 Sig Figs. My answer can only have 3 Sig Figs. So I have 348 grams of water for my answer there. So the overall thing that people get confused about is what to do with the temperature. The temperature tells you where to read the graph. And when you read the graph, whatever information you pull off of it, and it says this on the side over here, it's how many grams of solute dissolves into 100 grams of water. So as long as you can remember this, it's how many grams of solute dissolved into 100 grams of water, and you can set it equal to whatever he has in the question. If you guys have any questions, make sure you ask. Otherwise, have a great day.